Hello YouTube, this is going to be my first video on solving linear equations. We're going to get into kind of the basics here. But we're going to start with this. We say linear equations, they kind of get their name. You notice the root here of the word linear is line, okay? And so when we kind of talk about these further in algebra, we represent them graphically. You see that they represent lines, but they're pretty predictable functions. And so this particular class of equations, we spend a lot of time solving them, okay? So we say these are any equations of the form ax plus b, where we say a and b are constants, okay? So when we talk about ax plus b, something like this, we say this is a linear equation, okay? And it's always really easy to recognize a linear equation because you have some coefficient in front of a variable here. Recall that this number in front of a variable value is the coefficient of that variable plus some constant value. We refer to that as a constant, of course, because it doesn't have a variable. But we don't allow a to equal 0 in this equation, because if we did, think about this, this would be gone, and you just have some constant. We want a linear equation, and that looks like this. Okay, we say that any number is a solution to a linear equation if and only if the statement or equation is true when we substitute that number back into the original statement. Okay, and we also say that two equations are equivalent if they have the same solution. So for example, x equals 5 and x minus 4 equals 1 are the same. Okay, so we're going to talk about both of these. First things first, we say x equals 5. Guess what? This is an equation. And as a matter of fact, we don't even need to solve it. X is already by itself. And this is the first one I wanted to talk about here. Essentially, we're saying that a solution to this, we say 5 is the solution to this equation. But the reason why is because if we were to take that value and evaluate this equation, substitute x equals 5, substitute a 5 back in for x, we get this statement. We say, well, x, we'll take the x out, we'll put in the 5. We get 5 equals 5, and this is true. Okay, so the reason why x equals 5 is a solution to this is because when we substitute it back in, we get a true statement. And furthermore, we say x equals 5, this is the same as x minus 4 equals 1. And the reason why I want to say this is because what if I were to take this x equals 5 and plug in a 5 now for this x? We would receive this sentence here. We would say this is 5 in for our x value here. And we say, well, then I get 5 minus 4 is 1. I get 1 equals 1, and this is true. So we'd say this equation and this equation here, they are the same. And the reason why they're the same is because they have the same solution. So two equivalent equations. They are equivalent because they have the same solutions. And then last but not least, we're going to be following a specific set of what we call transformations. Of course, the word there being transformed means to change, okay? And so the nice thing about equations, I'll go ahead and pull this equation back over here, is this, all of these properties that we're seeing over here, they apply to equations, most especially linear equations. So we're going to use these all the time when we solve equations to get, say, something by itself. We could say get the x by itself. So these properties up here, we'll kind of look at the first one here, and I'll let you kind of prove the rest of them. But it says, well, if two things are equal, let's say a equals b, a number equals another number, then a plus c is equal to b plus c, because of course c and c are the same thing, and a and b were the same to begin with. So if I put c on both sides, and they were the same to begin with, then this should be the same thing still. So as an example here, x minus 4, according to this addition principle, I can add 4 to the left of this equation, so long as I say, well, this was equal to 1 on the right, and I want to add 4 to the right. And I'm allowed to do this because this is the same value, and these would still be equal. And the nice thing about this is, think about this, negative 4 and positive 4, they cancel out, I'm left with just an x. And on the right I get 5, which of course was the solution to this equation to begin with. So we're going to be using all of these properties here, but basically it says this: you're allowed to add the same thing to both sides. You're allowed to subtract the same thing to both sides, from both sides. Multiply both sides by the same thing, divide both sides by the same thing, so long as it's not 0. So let's go ahead and take a look at this first two-step equation. We refer to this as a two-step equation. Any ax plus b equals a number is a two-step equation, because really the only two steps we have to take to solve this. But we say when we solve an equation, our intent, our job, is to isolate or get by itself the thing that we're solving for. Okay, so when we consider this equation here, it's this proverbial find x. You could say, well, here it is, but we say find x, it really means get it by itself. So the first thing I want to do is this: I want to, 1, identify the thing being solved for. Okay, so we say over here, 1, we're solving for x. This is the first thing I want to establish here. 2, we say identify anything on the same side as that thing. And then that thing, sorry. We're going to eliminate these using our transformations up top. Using transformations, okay? Okay, and then we're going to isolate the unknown. So essentially in this equation here, when you talk about a two-step equation, really we're identifying the thing we're solving for. Number 2 here says identify anything else on the same side as x. I notice I have a 3/7 here and I have a positive 9 here. And in this instance, what I'm going to tell you is when it comes to two-step equations is always undo addition and subtraction first. Okay, I just want to make this clear. And then we say undo multiplication and division second. And that's for two-step equations. And the reason why is because it can get messy if you undo your addition and subtraction second and your multiplication and division first. So in this equation here, I noticed that I have two things in the way. We're going to start with addition and subtraction. So I noticed that this is a positive 9 here. I want to get rid of a positive 9. So we're going to do the opposite of add 9. And we're allowed to subtract 9 to do the inverse of that. But what we do to one side, we have to do to the other. And so in this instance, our 9's now cancel out. And what we're left with is this. We have 3/7 times x is equal to 15 minus 9, which is 6. So now to solve this equation here, I'm going to carry this down here. We say all we have left to do is undo our multiplication and division. And so now to undo multiply by 3/7, we're going to divide by 3/7. But the thing you want to remember is this: when you divide by a fraction, you really multiply by the reciprocal. So really we're going to take both sides times 7/3. And we end up with these things canceling out. We're left with just x on the left. And we say, well, in this instance, we multiply fractions straight across, but we notice that our 6 and our 3 can cross cancel. And we get 2 times 7 on top. Multiply straight across, 14. And then 1 times 1 on bottom, so 14 over 1, so we get 14. So the one thing I want to point out here is this. We're going to refer to this as a solution to the equation. And we want to check the solution. Okay, so step 4 here is to check the solution. And we check this solution by plugging it back into the original statement because it has to make the original statement true. So for instance, here we had 3/7 times x plus 9 is equal to 15, where x we just discovered is 14. Okay, and I'm going to put this 14 over 1, and the reason why is because I'm going to cross cancel these now. And I say, well, now 3 times 2 on top is 6. 1 times 1 on bottom is 1. 6 over 1 is 1, or 6. So 6 plus 9 equals 15. So this gives us 15 equals 15. So it must be a solution because it gave us a true statement when we substituted that back in. So that's how to solve a two-step equation.